There's more feedback from last week's lecture, which I can maybe use to get into today's lecture. Some positive comments. People quite like this geometric perspective on exponential families, which is good, because we're going to use it going forward into the next few lectures. And then there was a great question at the, about the content of the lecture. So maybe to recap, I'm going to use this question as an opportunity to recap a bit what we talked about before the break. I tried to sort of motivate it from the observation that we've been using a lot of Gaussians so far. I asked, well, what other probability distributions can we construct? We observe or we notice that there are these classic distributions that you've heard about in statistics courses, like the Poisson distribution, the Dirichlet distribution, the categorical distribution, and all these other ones. What is their common structure? Well, it emerges that we discovered together that they all fit into one common framework called exponential families, where each of these distributions, parameterized by a parameter, spans one such family called an exponential family, which is mostly, I mean, the operational part of these distributions is that there is a nonlinear function of the random variable in an exponential multiplied in a linear fashion with a weight vector. And that linear part in the weight vector then allows us to construct a lot of very interesting functionality, basically automatically producing a machinery for Bayesian inference and all sorts of associated statistical analysis, purely from differential geometry, so gradients, Jacobians, Hessians, on the log partition function of these distributions. And so the name of the game then boils down to, if you want to do general Bayesian inference, you just, quote unquote, need to know this one normalization constant. And so now one person wrote, well, nice, in your example, you picked one particular integral and said, well, let's treat that as a normalization constant. Now we get a probability distribution. But that seems backward. Normally, we have an application where we would like to say something about our data, and then that creates an integration problem, a normalization constant, which in general we don't know. So how do we deal with that? Well, so maybe first, the compact answer is you can't really in general, right? So I guess there's two options. One is you either restrict yourself to very specific probability distributions that you can find in a textbook that describe certain elementary phenomena, like IID Bernoulli experiments or categorical observations, or you create a general exponential family, and then you won't be able to evaluate its log normalization constant, and you'll somehow just have to live with that using some approximations. And in fact, in a backhanded way, that's what we're going to do today, and it'll lead us over the course of several lectures into a probabilistic perspective on deep learning. So what I want to do for the next few lectures is to take a new look at first classification problems and then more generally differentiable programs, deep neural networks, with you, and think hopefully in a little bit more careful way than usual about what probability theory has to say about these models. Now, when doing that, I'm facing a bit of a conundrum, just like in other parts of the course, which is that some of you, actually probably most of you, have already taken some other classes in which you've learned about, well, deep neural networks, algorithms for classification, and so on. So hands up, who's taken the deep learning class? Everyone, almost. Not everyone, but like 95% of you. Okay. So you've learned about classification, right? So what is a classification problem? I was told to be more interactive. So someone tell me. Yes. Oh, I should repeat the question. What is a classification problem? What type of machine learning problem are we talking about? Yes. So it's a super, I mean, I've only shown you a black slide, so you have to give a very general answer, which is great. So you're saying it's a supervised machine learning problem. So something where you get pairs of inputs and outputs, where the outputs are, well, discrete, right? So they might be binary or multi-class. So there are problems like this, right? Who has seen this data set before? Just to make sure I'm staying correct. It's not even everyone, but it's, okay, 80%. So this is a common toy problem. It's not even a benchmark. It's just a toy problem, which I'm going to use, actually. And here, okay, so maybe the main reason to show you this is, so this is called the 2 moons data set. We're going to use this today to test our code. The nice thing about it is that it's 2-dimensional, so we can look at it and look at the output. It's obviously extremely simplistic and very far removed from, I don't know, like autonomous driving, yeah, where you have to classify some some camera images into pedestrians and kids and so on. So I'm going to, over the course of this entire semester, stick to simple problems like this. This is not because I don't, like, I think real-world problems don't matter. It's for 2 reasons mainly. One is you already have taken these other courses, so I hope that my colleagues who are teaching the deep learning class and related more advanced classes are equipping you with the tools to work with much larger problems. Secondly, this allows me to do experiments here in the Jupyter notebooks in 30 seconds. And we can just look at output and play around with it and get a feeling for it, which is much harder if we're working on ImageNet, right? Where I would need like a GPU machine and wait for hours to train something, and then, yeah. So it's really not that I realize that I think this is how the real world problems look like. No, it's just very convenient to use as a toy problem. We're still going to write code that in some sense generalizes to much higher dimensional problems. So this is one particular classification problem. We have an input space, 2-dimensional. There are inputs in here. Every dot on this plot is an input. And that input is supposed to come from 2 different classes: the yellow, orange filled circles and the blue empty circles, class 1, class 2. And now our goal, well, what's actually the goal in classification? Well, what are we now trying to learn from this data? Yeah. Maybe the class structure. So what would the class structure? So the class structure, is that a function of the input space or the labels? Or well, I mean, it might be both, but is it predicting inputs or labels?
Well, I'd say if you have the function, like the class structure of a class already given, you want to predict the inputs, not the labels, because you already know it.
This is a very interesting point. Actually, I think typically we talk about it the other way. So the sort of your knee-jerk reaction to classification is, I want to have a function that maps from this 2-dimensional input space to labels. So if so that I can ask this function here, what's the class? Is it blue or orange? Right? And then the output, well, in a case like this, which is arguably a separable data set, right? So there's no overlap between the classes, might even be a binary thing. You could, the classic answer 50 years ago would have been 0 or 1. It's either blue or orange. And maybe, I don't know, somewhere around here it's clear that the answer should be blue, and somewhere around here the answer is clear that it should be orange, and out there, well, it's a bit more complicated, right? So maybe we want to have predictions that aren't actually 0 or 1 binary, but they are more grayscale, yeah? So probabilities between 0 and 1. And maybe that's a first way to use probabilities in classification, but it's the boring way. It's just, yeah, okay, we need to predict with something between 0 and 1. But there's actually another question, which you just raised, which is sort of the opposite, which is to say, what is actually the distribution of the blue dots? So you can think of this as a conditional distribution. Given that I know I belong to class 1 or class 2, where am I in this space? So That's a generative question. It says, make more of the orange stuff. Make something that looks like the orange stuff. Such classification problems are typically not as easy as this. So this is sort of your textbook problem from the 1960s. Here is maybe a slightly more realistic classification problem. It's a multi-class problem with 3 different classes, blue, orange, green. And what you can, well, okay, what's a feature of this problem that makes it harder than the previous one? It's one of these questions that are so easy that probably nobody even wants to answer it. So I'm not going to embarrass you by forcing you to say something banal. The classes are overlapping with each other. Yeah? And so clearly here, probabilistic output is going to be more important. So up here, we probably want to be sure that it's the green class. And down here, we probably want to have like a 50-50 thing between orange and blue, but a low probability for green, and so on, right? So I can actually tell you how I made this plot. It's an ever so slightly more realistic example. This is actually a 3-class classification problem that I created by taking a higher dimensional data set with something like, I don't know, 120 dimensions. I think it's actually pixels, 28 by 28, that have grayscale values, and then I did principal component analysis on them, and these are the original images. It's not MNIST, it's this even simpler digits problem from SciPy. So here's a 3, here is a, I don't know, maybe that's a 1, and that's a 4, I guess. And these 3 circled dots correspond to these 3 images. So, of course, right, possible classification problem, maybe I give you an image, you tell me what I'm looking at. A 1, a 2, a 3, a 4, and so on. Most generally, we might have some space, densely packed with points, or not so densely, in some regions more densely, in some regions less densely, and we would like to do 2 different things. We'd like to know, given an input x, so at this point in the space, what is the probability distribution over the labels, 1, 2, 3, and so on. Or the other way around, given a label, orange, what's the distribution over the inputs? So that's, of course, what I hope you've encountered in various other courses as well. In a deep learning class, maybe in a statistical machine learning class already. So because almost all of you raised your hands when I asked who took the deep learning class, I'm guessing the following definition is going to be relatively obvious to you. And what I'm going to try and do today is to imbue these typical objects that you encounter in deep learning with a little bit of probabilistic interpretation. And maybe that helps understand classification better. It'll certainly help as a precursor to constructing a probabilistic perspective on deep learning, where I will have good arguments for why you might want to have one. So how does classification look like in deep learning? Well, it looks like, before I show you the definition, some complicated piece of code that involves things like, okay, so a data loader, fine, we'll talk about data loaders later. But then a model, some multi-layer perceptron, some convnet, some whatever, encoder, decoder architectures. A loss function, and or link functions onto the data. Then some algorithms operating on that loss function, computing gradients, following those gradients to minimize some empirical risk. And once we've done that, we have a trained neural network, which we can use in a forward mode to make predictions, to compute things like logits, and then push them through softmaxes and logistic functions and so on, right? So let's try and tease this apart and see how much of this structure, which, I don't know, if you're like me, you might think that these things, at least in the deep learning world, they often kind of drop from the sky somehow. They're just there. Logistic, softmax, whatever, where they come from. Let's see if we can motivate them from a probabilistic perspective. So here's my definition of the classification problem. We're considering a, as you said, supervised problem. So we'll have pairs of inputs and class labels. The inputs come from some space, X. Let's, for simplicity, assume that they come from a real vector space of d dimensions. So in my case, the 2-dimensional plane. But in general, it could actually be anything. Could also be strings and graphs and whatever. And then we have, for every individual datum, also a label. And that label comes from a subset of the integers. It's either plus minus, binary, and then we can isomorphically map plus minus in various ways. It could be 0, 1, or plus minus 1, or yes and no, or success or failure, or whatever. Or more generally, it comes from a set of multiple possible categories. 1, 2, 3, 4, 5, all the way to k. Capital K is going to be the number of categories. And so if we want to have a probabilistic description of this overall process, we're going to have to inject probabilities here somewhere now. So what we're going to assume most generally is that these data, they come from some joint distribution, P of x and c. And then actually we'll immediately do the first approximation or simplification that everyone does, not just in probabilistic inference, but also in deep learning and everywhere else, which is the assumption that this data comes IID, so independently, identically distributed from this distribution P of x and c. Because otherwise we'd have to worry about the order in which the data arrive and interdependency between the data points and so on. Generally, we don't even want to do that, let alone actually know how to do it. So if you have a joint distribution, you know from lecture 1 that you can turn a joint using the rules of probability into conditional distributions. And two of those, the two related conditional distributions, are the interesting ones, right? We want, on the one hand, to be able to predict class labels given inputs. That's called a classifier. Or predict inputs given class labels. You could call that a conditional density or a data density or a generative model. Yeah? So in the most extreme case, you could imagine I want to give a string that identifies a class, a string that says, I don't know, dog in an astronaut's spacesuit dancing on the moon, and the conditional density should be the pixels of an image that show this particular scene. Or more simplistically, in my examples, I want to say class 1, and it produces a little thing that looks like a moon, one of half of the two moons. So now let's see how far we get with just Bayes' theorem. So let's say, first for a moment, let's say we have a binary classification problem. So k is 2. There's just two possible answers. Then we can write down first the classification task. So the probability for one of the classes, let's say the first one with loss of generality, is, well, Bayes' theorem. So it's the probability for that class prior times the likelihood, so the P of x given the class. This up here is the joint distribution given c equal to 1, right? So that's P of x comma c equal to 1. And then the normalization constant, the evidence, just has to consider two possible hypotheses because there are only two classes. So probability likelihood for class 1 times probability for class 1 plus probability for class 2, given that times the likelihood for x given class 2. So we know that those have to sum to 1. So we can write this as 1 minus P of, well, this thing here, because the whole thing integrates to 1. And now we can observe some structure here. Namely, this term shows up both here and there, right? That's the same. So we can divide by that. We'll get 1 over 1 plus a ratio, that's down here, of two probabilities. Now, probabilities are numbers between 0 and 1. So a ratio between two numbers between 0 and 1 is another positive number. And you can write every positive number as the exponential of something, right? And that something is given by, well, if you write it as minus something, then it's the logarithm of this so-called log odds, or of this odds ratio. So the odds are ratios between two probabilities, just like if you go sports betting, right? So the probability for one class, given the input, is naturally 1 over 1 plus the exponential of minus a, where a is just something. A happens to be the log odds. And that thing is called the logistic function, right? So everyone has seen logistic functions before, yes? So they don't just drop from the sky. They are not just some sigmoid that it can be thought of as, I don't know, a cumulative density function of some distribution. They're just a natural output of Bayes' theorem. If you have two possible answers, Bayes' theorem says you're computing the logistic function of something, and that something actually happens to be the log odds. Yes? What motivates the 1 or the minus sign? Well, so I think the main motivation for the minus is that, so if you think of this thing, right, so if a goes to infinity, you get 1. And if a goes to minus infinity, you get 0. So you want this a to be something associated with the first class when it has high value. That seems more intuitive, right? If a is a description of the class, and we tend to think of the positive class as the thing we're interested in, then you want to have large values of a associated with that class. Otherwise, it would be a bit weird to say very small numbers correspond to high probabilities. So that's just why you put a minus there. I mean, what this does is it just changes the order of this. Right? It just inverts this ratio. By the way, of course, you can compute the inverse of logistic. You can do that on a piece of paper. You find out that that's the equation to compute, and that's why this is called the logit, the inverse logistic transform. But I think it's actually a lot better to think about this as the log odds, and it's just as arriving from Bayes' theorem. Okay, so far, not so much new. We just now know that there's this one thing that shows up in classification, the logistic function, that we now realize isn't completely arbitrary. It's actually just Bayes' theorem. Someone is applying Bayes' theorem. But what are they applying it on? Well, they're applying it on their big model that they've trained, right? Your deep neural network. Where does that deep neural network come from? So here's another cool trick that connects to the last lecture. So here I've copied over the line from the previous slide. So now let's do a second thing, and let's make an actual assumption. Let's say that we assume that our true class densities, so the piece of x given class C, that those are exponential family distributions. So remember that an exponential family is just an exponential of something nonlinear in x times some linear in parameters called the natural parameters minus a log normalization constant plus a Bayes measure. Then if these are the class distributions, then we can go back a slide, or actually just go up one line and see that, oh, for classification we need these log odds. Logarithms and exponentials, nice. There's something is going to cancel. So let's write down A. A will now depend on the natural parameters of our exponential family, and it'll be linear in those natural parameters. So we can write our log odds as the features of the input times something linear. It's a difference between the two classes for our binary class problem, plus something constant that doesn't depend on x. And then there's also, h of x, which I'll just pretend is 0. It's just a Bayes measure, or we can just plug it in here if we really wanted to. We would just add something h of x with a 1 next to it. And then, of course, we need the log priors. So these are the probabilities for the classes, but that's just a constant. It's just a shift up and down, right? So that means if we assume our class conditional distributions are exponential families, then the input into the logistic function will be a linear map of some parameters, multiplied with a bunch of features. And those features describe the exponential family. They describe a probability distribution over the inputs. So that's a motivation for something that is linear in parameters. Admittedly, maybe it's a bit like clasping at straws, Why? Well, first of all, I made a strong assumption to say it's an exponential family. Secondly, I'm assuming it's an exponential family, so this is actually a probability distribution. What I would like to do, of course, is the other way around. I'd like to say every time someone uses a linear classifier like this, they are actually making an exponential family assumption about their data. But that's not generally true, because in deep learning, you might encounter feature functions here, phi, which don't actually give a probability distribution, because they're just not normalizable. Right? You might have choices of theta associated with parameters phi, such that this g doesn't exist. It diverges. It's infinity, right? Plus minus infinity somehow. So in general, that doesn't work. And actually, I think that's not a problem with my argument. It's a problem with deep learning. Because maybe occasionally you want to make sure that your model is consistent in the sense that it only puts finite probability mass over each class. We'll talk more about that in later lectures. But for the moment, we just have to say, if this is true, then our model will look like the last layer of a deep neural network, right? The logits of a deep neural network, a logit layer. And the other way around, if our network has this structure, then it almost looks like an exponential family over x. Yes? Yeah. So the question is, where is it? There's no deepness here, right? It's actually not a deep neural network. It's just a neural network that is linear. It's actually a linear model, a model linear in the parameters. So in a deep neural network, those features phi will depend on further weights, deeper layer weights. And I will have to ask you to wait until next Thursday. So not 2 days from now, but like, I don't know, 10 days from now for us to get to that point. So for the moment, we'll just assume that we only have a linear model. But we've just realized is that one way to motivate such a linear model is to say, oh, maybe my class distributions are exponential families. Actually, does this also work for multi-class? Yeah, it also works, and it gives the maybe predictable answer. So if we have more than 2 classes, then Bayes' theorem will look like this. So the probability for class number k given x will be prior times likelihood divided by, well, the normalization constant, right? So the sum over all possible choices of classes. And it'll be a sum because there's finitely many classes. So it's a discrete sum. And those are numbers with, like this is a positive number, that's a positive number because they are probabilities, they integrate to 1. This whole thing sums to 1. So you can think of this as a sum over individual terms for each class, and then a final term that is 1 minus the sum over these classes. And all these numbers then supposedly are less than 1. And so we're actually getting something that could be thought of as an exponential of some number between some real number divided by a sum over the exponential of some real numbers, and that's called a softmax. So whenever you encounter a softmax somewhere, someone has used Bayes' theorem. They just might not have told you about it. The softmax is not some like smooth approximation to the maximization function. It's just Bayes' theorem. Or maybe if you like this interpretation of a smooth approximation to max, then Bayesian inference over finitely many hypotheses is just softmaxing. And that's actually another way of thinking about it. So instead of making a hard commitment to one particular hypothesis, we're distributing probabilities over these different hypotheses. So the softmax is just Bayes' theorem. And correspondingly, if we assume that each of the class conditional distributions comes from its own exponential family distribution, then this A that goes into the softmax, which is the logarithm of these probability distributions, just cancels the exponential in the exponential family, and we get individual classifier models, logits, that are linear models. And I will now use the symbol theta for this, hopefully through the entire set of slides. If I don't, and there's a W somewhere, then I apologize in advance. So from now on, we're thinking of, in general, the parameters of some linear model. Yeah.
So
Say again? Ah, great question. So you're saying, what about the conjugate prior to this exponential family? So is that the prior for the class C, P of C? Is that our conjugate prior? Actually, no, because so this is a really great point to make. So we are assuming that for every individual class, we have a probability distribution that is an exponential family. So it has to be a probability distribution for each class. And it could be, and we don't know what that distribution is, right? So that class will have parameters, WC, which I'm thinking of as a subset theta k of the parameters of your linear model. And along each row of this theta matrix, right, along each k dimension, we want to have a conjugate prior. But we're going to have different conjugate priors for each class. And so we'll need another thing, something P of theta k. That should be the conjugate prior. And so far, we haven't talked about that. We're just assuming that there is some correct choice theta, and we haven't done inference on it at all. And actually, that's a great point. We'd like to make this connection and say, if you're training a deep neural network, are you actually somehow doing maximum a posteriori, maximum likelihood type inference in some exponential family distribution? Well, if you're training a shallow neural network. And that's what we're going to do for the rest of today's lecture. So here's a quick summary. The first thing is just we've discovered that the softmax and the logistic transformation are natural results of applying Bayes theorem to supervised classification problems. If you're computing conditional distributions for a discrete set of finitely many hypotheses, Bayes theorem is always a softmax. It's a very generic structure. And the special case of a two-dimensional softmax is the logistic. Now, additionally, if we assume that the class conditional distributions, so the P of x's given C, are exponential families, then the corresponding logit model is a linear model. Or in fact, we can almost turn this around and say, whenever you're using a linear classifier, phi of x times some parameters, then if that same thing now if these phi of x's happen to have the property that they can actually be integrated over the input domain and give a finite number, a log partition function, then they are exponential families. Now, if they don't do that, if the features are such that you can't integrate over x and get a finite number, well, then you just don't have a class conditional distribution. Your model just doesn't allow you to predict x's. And that's not a problem with Bayes theorem. It's just a problem fundamentally with probability measures, right? If you have a model that doesn't produce a probability distribution over x's, then you can't generate more x's because there is no way to meaningfully define samples. Okay. Any questions on this? Am I a bit too slow, I'm sensing? Can we go a bit faster? Oh, no, it's good. Okay. Some people think maybe a bit faster. So now so what we've done so far maybe is just motivated some choices in the architectures of deep learning. We've motivated vaguely the model class and the loss, right? So the fact that we have softmaxes and corresponding cross-entropy losses, so cross-entropy losses are just logarithms of the softmax, we get from Bayes theorem. And at least the last layer of our neural network, this linear last transformation, we get motivated by exponential families. Now there is this operational part of deep learning, minimizing some risk, minimizing our cross-entropy loss on the labels. Can we somehow motivate that from a probabilistic perspective? Well, the natural thing we're going to be looking for is that we're somehow minimizing a loss should somehow be the same as computing a maximum likelihood, maximum a posteriori distribution on the parameters theta of our collection of exponential family distributions. So we'll do that. And this is, in this simple linear case, connected to the idea of logistic regression. So who has heard of logistic regression? Not everyone, but large parts. Okay. So, well, apologies to those of you who are seeing something you've seen before. Maybe it's also good that occasionally there's something that's a little bit slower. So we're now going to assume that we have a function f that takes in inputs and parameters theta that has this linear form. I'm introducing this function f already because, of course, in later lectures, this will be our network, our differentiable program. And it will have a more general structure. But it'll remain this function of two things that you can also think of as maybe a second order function, something that takes inputs x and parameters theta and then produces a prediction. We're now going to make the specific assumption that it's linear in the parameters for the moment and nonlinear in x. We call this the features. Then this is in particular true if x is actually from an exponential family, but that's a special case. For that, we also need that the integral over phi of x is a finite number for any particular choice of theta from the domain. So now there is an annoying notation problem that is commonly dealt with on a slide like this one. Let's say we have binary classification problems. So we have two possible labels. Those labels could be plus or minus 1, or they could be 0 or 1, or they could be 1 or 2 for class number 1, class number 2. So we are going to now, for the rest of today's lecture and also next week's lecture, assume that the labels y are signs. They're plus or minus 1. Why is this convenient? It's convenient because the logistic is symmetric around the origin. So in the sense that sigma of x is 1 minus sigma of minus x. They sum to 1. So that allows us to write the output of the classifier for both classes, for y equal to plus or minus 1, as a single logistic transformation. So sigma here is our logistic, 1 over 1 plus e to the minus x, or 1 over 1 plus e to the minus the input to the function, where we now just multiply with the class label y. So this sort of takes care of both cases, sigma and 1 minus sigma in one go. And to make notation easier over the next few slides, I'm going to combine feature and label into a symbol var phi, so that the other phi Greek character, so that I don't constantly have to write y times phi. Okay, so this is going to be, from the learning perspective, so from trying to figure out, given some training data, what the classifier should look like, as a likelihood. So here's a probability distribution over the labels, given the parameters, and we're now going to try and infer the parameters theta. So this is actually now very similar to the other type of supervised machine learning problem we've encountered so far, which was regression. Right? In regression, we also had outputs y. The outputs just happened to be real numbers. And then there was a function with weights theta. And in regression, this was a Gaussian distribution that had a linear map through theta. We still have this linear map now, right? So this looks a lot like what we had in regression. But unfortunately, our likelihood is not Gaussian anymore. And so things are going to be a little bit more complicated because we're not going to get a closed form Gaussian posterior. So what might be our knee-jerk reaction is, and I'm going to show you this picture and then we'll take the break, is that we would like to say, we're going to put a prior over theta. I don't know, let's put a Gaussian prior because we like Gaussians. Gaussians have great analytic properties. Then we have this linear function of theta. That's great. That looks a lot like regression. It's actually the exact same setting. And the only thing that's changed is that the likelihood, this term in Bayes' theorem, is not a Gaussian anymore. And so it's not going to work anymore in closed form. We're not going to be able to just multiply a Gaussian with a Gaussian, make use of all these great properties of Gaussians, and then somehow everything pops out automatically. We'll have to be a little bit more careful. So if we write down Bayes' theorem, even with a Gaussian prior over the parameters, then in the likelihood we'll have a lot of these logistic functions, and our log posterior will be a quadratic function plus something non-linear in phi, the logarithm of a logistic. And that just stays in this form. There is nothing we can immediately do to simplify this. To show you a picture of what I mean, but yeah, question?
So you say that the posterior is not Gaussian, and that's a problem, but then you use a Gaussian posterior?
A Gaussian prior. So actually, after the break, I'll try and make the connection the other way around to the exponential family bit that we've done before the Pentecost break. But yeah, let me maybe just finish this little story here to maybe also with a bunch of pictures. So what I'm showing you here is, okay, maybe I need to explain this picture for, actually, you know what, let's take a break now, and then I'll need 5 minutes to explain that picture. Up. Let's meet again after the break, and then let's see if you have some questions until then. I realized over the break that, again, maybe this is something that I should have prepared a slightly different way, but maybe let me see if I can still, without changing the slides, get you back onto this. So there's now, given the arguments that I've tried to make in the first half of the lecture, we can now approach the problem of learning a classifier from two different motivations. Let me do them separately from each other. The first one is the motivation that I'm currently following, which is maybe sort of a knee-jerk thing coming from what we've done about Gaussian regression in the earlier lectures. So in lecture 3, 4, 5, 6, we learned to work with Gaussians, and we learned that we can use Gaussians to learn functions. And the mechanism for that was, let's find a linear model, so something like this, where x's are the inputs. We would like to learn a model that maps from x to a real number y. Let's use a Gaussian prior on theta, and let's use a Gaussian likelihood for y given f of x, and then everything works fine. So now we're going to try and do this here again, where the only change is that the likelihood is not Gaussian anymore. The model is still linear, the prior is still Gaussian, but the likelihood is not Gaussian anymore. And then things will get a little bit more hairy, and we'll need to resort to approximations. So the other perspective is from much closer in the course, from before the Pentecost break. We spoke about exponential families. And I just motivated the use of a linear model from the exponential family perspective. And said, what if the distributions over x are exponential families? Well, then we get this distribution, which has natural parameters. Sorry, not this distribution. We get this classifier, these logits in our binary classifier, the log odds, which are a linear term, and those thetas can be thought of as the natural parameters of an exponential family. And before the break, I spoke about the natural conjugate prior to an exponential family. So now your question could be, well, what's the conjugate prior? Why aren't we using the conjugate prior? Why is there no conjugate prior on this slide? So the problem with this is, let me just briefly go back, is that if we wanted to do this, then our exponential family will look like this. And you will remember what the conjugate prior of an exponential family looked like. It was another exponential family that had as its sufficient statistics those parameters w and this log partition function g. We need that to construct a conjugate prior. And here we don't know what it is. We would need to know the integral over this expression, so with the exponential over dw to get this number. And in general, that's going to be a super hard integral to do. So we don't want to make this constraint of assuming that we know what this g of w is, and so we can't hope to directly construct a conjugate prior. Instead, we'll go sort of down this simpler route of saying, well, how far can we get with the mechanism we learned about Gaussian inference? to give a pictorial view of this, why this is slightly harder than before, here's a picture that I could have also shown when we talked about regression. So here is, and here I need to explain what this weird picture is. So let's say we want to learn a function that maps from an input space, x, in this case it's just a real line because I can make a plot in the real line, to an output space. And in regression, that output space used to be the real line. Now it's the simplex between 0 and 1. So a probability between 0 and 1. What I'm going to do is I'm going to put some features over this input space. Here in gray, I've used one particular class of features that we've encountered before, ReLUs. Why ReLUs? Well, because they are somehow have something to do with deep learning, right? We now also know that they are associated with some interesting stochastic processes. They give rise to cubic splines in the infinite limit. You can motivate them from integrating Brownian motions, so particles moving with momentum and so on. So here are just a bunch of features, 1, 2, 3, 4, 5, gray lines. Each of these gray lines is a 0 all the way to some point, and then it becomes a linear function. So now let's talk about the covariance under a Gaussian prior for the function value at x1 and x2, sorry, for the function value f of x, where f of x is phi of x times weights. That's a Gaussian distributed random variable. And we can get it from taking a prior over the weights for each of these features and then pushing it through these features, computing the push forward. So taking our Gaussian and multiplying it with phi of x, basically. That will give you, in general, correlated Gaussian distribution over the function values at x1 and x2, which I'm showing here. So this is f of x2 versus f of x1. And in general, that's just going to be some Gaussian. Yeah? With marginals that are, of course, Gaussian, because the marginals of a Gaussian are always Gaussians. Now imagine that I want to condition on having observed a single datum at x2. So I observe that this function value here is somehow connected to a likelihood term associated with one positive observation. So my likelihood is this logistic function. I observe that here I have a positive observation. I get a label 1. So I need to multiply this Gaussian prior in gray with this likelihood function that is this orange thing now. That's this logistic, right? The logistic is this sigmoid function. So I need to multiply this gray thing with this orange thing. Well, and that gives me this. I've just done this here in 2D. I can do this numerically. I've just multiplied these two distributions with each other. But in general, that's a nasty distribution. So you see here this red thing here. That's the posterior over the two function values, f of x1 and f of x2. And if I project those to get the marginal onto x1 and x2, you see that they are not Gaussian. Right? They're not Gaussian. Okay, does everyone follow? Is there a question about this plot? Yes? Yes. So those are the features from before. Yeah, sorry. The features, so I'm plotting two things. This plot should probably have two different y-axes. So it's a bit complicated to plot all of this in one plot. So this label is supposed to correspond to these gray feature functions. And then there's an underlying function here that is this gray distribution is associated with, which is real valued. So there should be maybe I should have put the phi over here and put a second y label that goes from plus minus infinity, a real number. And now I observe something. Remember that our observations in a classification setting are binary, or at least in a binary classification setting. So I need to plot them somewhere, and I decided to plot them in the same plot. But they're in a different space, right? It's just a 0 or a 1. Okay, so this, maybe just ignore this line at 1 and this yellow dot, then the plot makes sense. Right? So In Bayesian inference, we have these logits A. This is a function, a linear function of the input, and A is a real number. But the labels we get Y, they are 0, actually they're plus minus 1. So they're just one out of two possible choices, right? So I don't even need to make a plot for that, because why waste an entire axis for something that's just one out of two possible answers? I just need to put the fact that I've observed 1 somewhere. So maybe I shouldn't have put this yellow dot here. I should have just said, I've observed that over here there should be a positive label. And then you get this likelihood. The gray lines are the phi of x's that when multiplied with the, okay, maybe the plot doesn't actually help. So let me just go back. There is a bunch of features of x. In this plot, these phi of x's are piecewise linear functions. We lose. We lose because it makes a connection to deep neural networks. So far, they're just shallow. Yeah? And then there's a bunch of parameters theta. We're putting a Gaussian prior over the parameters theta. That implies a Gaussian prior over f, because it's a linear map of theta, and any linear maps of a Gaussian distribution are a Gaussian distribution. So this function under this assumption is Gaussian distributed. Our observations are labels, y, they are plus minus 1, and they enter through this object curly phi into the likelihood, where phi is literally just y times the other phi. So it's just either plus or minus. So if we observe positive labels, we can just think of these two being equal to each other. And now the challenge is not that this is a nonlinear function of x. The challenge is that this sigma is not a Gaussian. So it's not a quadratic function in phi. And the product between an exponential of a quadratic and a sigmoid is the same as the exponential of a sum of a quadratic and something non-quadratic, namely this thing. And that just looks like this red curve here. And now we need to somehow deal with that so that we can get some closed form expression for this red distribution, at least approximately, that we can actually write down without having to make such a complicated plot for everything that's going on. Yeah. Yeah, so for this particular plot, I've chosen some very basic Gaussian prior. So I've set the prior mean to 0, which means the prior mean for f of x is 0. And I've used a standard prior for the weights, unit covariance. It gets pushed through these softmaxes, which makes them a bit wider. So, right, because they are piecewise linear. So now we have something in the order of, you can see that f of x1 has a smaller prior variance, actually, I think, because it uses less features. So this is slightly wider, but yeah. I mean, it's really just the way I made the plot. So the point of this plot is to show that the product between a Gaussian and a logistic is not a Gaussian. That's the main thing here. And in 2D, for two different function values, I mean, I can plot the posterior distribution. That's the red line. That is the posterior distribution, this red contour plot. But we want to use this as a mechanism to learn functions over many possible outputs, right? Over maybe we'll have 10,000 training points or 100,000 training points, and we want to predict at arbitrarily many points afterwards. Then we cannot make a plot like this. Doing this would be exponentially expensive in the number of training points and the number of test points, which is why we need something simpler. We need to project it back down into some description that we can keep track of even as we scale the number of inputs and the number of test points. And the way to do that very naively is to find that red point. That red point is the mode of the distribution. We can find that point with optimization, with the exact mechanism you know from deep learning. Some optimizer finds that red point. And then at that red point, we're going to do something extra. We're going to measure the curvature of this red distribution at that point. And that curvature, well, actually the curvature of the logarithm of that distribution, will give us the inverse covariance of a Gaussian distribution that we can then use as an approximation for this red thing, and that's called the Laplace approximation. And that's, again, the connection back to exponential families, where we did the exact same thing. We're just going to keep using it. So here's how this works. Assuming, so this is, I think, the third time I'm doing a Laplace approximation, so I'm going to get a little bit faster, but the slides are now also more and more abstract, so maybe they get harder to follow. Consider a general distribution over theta, in particular maybe the posterior that we just encountered, which we can't track fully. To construct an approximate probability distribution rather than just a point estimate, you do the following. You first find a point estimate. To do that, you minimize the negative logarithm of the probability distribution, which is the same as maximizing that logarithm, which is the same as maximizing the distribution itself, p of theta, because the logarithm is a monotonic transformation. It doesn't change the location of the mode. We do that, how? Well, with optimization. We compute a gradient of the log of the probability distribution. Remember that the logarithm of our probability distribution is going to be something linear in the parameters. We'll set that gradient to 0. That will effectively ask us to solve some implicit equation. And then at that point, where theta hat, where the gradient is 0, where we are at the mode of the distribution, we will perform a Taylor approximation to second order. So we will compute a constant term, that's the height of the logarithm of the distribution at that point, plus a linear term, which is 0, because the gradient is 0, plus a quadratic term, which looks like this. So it involves a delta, where delta is the shift away from theta hat, the residual, and then a Hessian, a curvature matrix in the parameter space. And then we can think of this as the logarithm of a probability distribution, where the corresponding probability distribution is e to the minus this. And actually, no, it's e to this, right? The exponential of this. So that's constant times exponential of a quadratic, and that's a Gaussian. Where the mean of the Gaussian is equal to this point estimate, and the covariance of the Gaussian, just from the definition of the Gaussian PDF, is the negative inverse of this Hessian. So for our linear classifiers, ever so slightly more complicated, we do the same thing. We take our log of p, which is now our linear function in theta. We minimize it to find a theta star. We find its Hessian, invert it, put a minus in front, and that gives us a Gaussian distribution over theta. Now, to make predictions at other points, at new x test point, we can do this generally because we keep our distribution over theta, and the relationship between the function at one point x and another point x prime is mediated entirely by the features. So to make a prediction about the function value at some other point, well, we just use the fact that our function is given by this linear term, phi of x transpose times theta, and we marginalize over our approximate posterior over the parameters, which is a Gaussian, and use properties of Gaussian distributions, namely that they're closed under linear maps and marginalization, meaning that our prediction at some new point x for this latent function f, for the logits of our classifier, will be a Gaussian where we just multiply the new features onto the estimated posterior mean, our map estimate of the parameters, and multiply the covariance from the left and right with the new features. Why is that interesting? Well, we can compare this to what we would do if we actually had the full posterior over the parameters theta. And because we get this linear form in f of x, you can convince yourself, and I think that's an equation you have to stare at for a while, and there's not much point in me explaining it, but basically we're integrating over the fact that f of x is a linear function in theta, So therefore, you can simplify the integral and get everything, like do an integral over just the distribution over theta. And we'll see that the analytic form under the assumption that we have a linear function phi of x times theta would make a point prediction at some new point x that is given by these features of the new point times the expected value of the parameter theta. We don't have that expected value. We've approximated it with the mode. And you can do the same derivation for the variance. The only thing that's changing in this slide from the previous one is this last slide, to convince yourself that the same holds for the variance. So the point here is what we're doing when we're using a Laplace approximation is, in a linear model, is actually a very mild kind of fix. Namely, we're replacing the actual mean and the actual variance of our parameters in the posterior, which we can't compute in closed form, with point estimates given by the mode of the distribution and the curvature of the distribution at that point. But other than that, we're making no further simplifications. That works if the model is linear. If the model is not linear, it's not quite true anymore. So that gives us a distribution over the latent function phi, but not over the class labels. To make that prediction, so to predict the label of a new input at a new point, I need to do one more integral, but there's a question before that. So the question is, we can continue to use higher moments to when will this hold? So I don't have a slide for that, so let me do a spontaneous kind of answer. So for Gaussians, it's true that the higher moments are just analytic functions of mean and variances. So we are going to, actually, I think for, okay, maybe the short answer to your question is for higher order moments, this is not exactly true. So for higher order moments, you will get an expression that is of the form something phi of x from the left and phi of x from the right to higher order. So you'll get 3, 4, 5 phi's entering, right, of the order of the moment. And then inside, you'll have the corresponding higher order moment of the posterior. And we're going to approximate that higher order moment with this analytic expression of mean and mode and curvature. So there will be no new quantities entering, right? So we will, sort of by the nature of a Laplace approximation, we're only using the location and the curvature. So you can write these expressions, but in here you will get pretty much something like theta times theta Hadamard with sigma, and then sigma Hadamard, or outer products with sigma vectorized, something higher order tensors involving sigmas and theta hat. Yeah, not sure that helped much, but so the structure of this approximation is that the phi's will always stay in here in the right order for the moments, but the moments inside will be approximated, I would say, to a more and more vague degree. So how do we make predictions? So the slide will stay the same, just the last line changes. To make a prediction for the label, so the probability to get a 0 or a 1 if we ask for a new label at a particular point, that's the expected value of the logistic of phi, which is just an integral, which doesn't have a closed form expression. So what you can do now is you can somehow come up with another extra approximation to this integral. The simplest possible approximation is to just say, oh, let's just plug in our point estimate here. And that's what we typically do in deep learning. Right? We've trained our network, we've got a theta star, and we just plug it into the sigmoid, and that gives us a prediction at a new point. Notice that this expression does not use the posterior covariance at all. which is exactly why it is used in deep learning, because in deep learning, this posterior covariance doesn't mean anything. It's not, well, it means something, but it's not typically used. And that means, one way to interpret that is that using this kind of approximation that is commonly used in deep learning ignores the uncertainty over the parameters. So if you have a high posterior uncertainty over the parameters theta, you probably should be somehow typically less certain, less confident about the label, and you won't get this if you use this approximation. More generally, you would like to do this here, where Q is some distribution. And even if this is a Gaussian distribution, we don't know how to do this in closed form. So we'll need to come up with other approximations that somehow are better than this, and we'll do that later, or next week. But we might be able to do that because we can maybe convince ourselves that this is a univariate well, sorry, no, it's not a univariate integral. It's an integral over a high-dimensional theta, but over a univariate number. So that might make the integral a bit easier. Okay, so we're almost done. I just want to show you some code in the last 20 minutes. So what I've now done is I've approached the problem of classification from a probabilistic perspective. We've discovered that that some structures commonly used in deep learning re-emerge. Linear models, logistics, and softmaxes. And we're now trying to make a connection to the final step, the actual learning bit in deep learning. In deep learning, we find point estimates for a parameter vector theta. And I've now just motivated making such a point estimate by maximizing a posterior distribution. Taking a prior over the weights, times a likelihood, taking the logarithm of that, finding the mode of that distribution. And then at that mode, to get a posterior output, we do something extra. Namely, we measure the curvature of the posterior at that point, just to add a modicum of probability of some description that goes beyond just the point estimate. That's called the Laplace approximation. And the common criticism that you will encounter actually if you talk to Bayesian deep learning people will be what's on this slide. Namely, that Laplace approximations are very dangerous in some sense because they can be arbitrarily wrong. What do I mean by arbitrarily wrong? Well, let me go back to this picture. Here's maybe where the picture is actually useful. So we're approximating this complicated distribution with the mode, so that's the highest point, and then the curvature at that point. I haven't actually plotted this in here, but I'll show you a picture in a moment. And that this distribution may be missing a lot of the mass in the tails here if this curvature is very high. So let me go back to this picture. If you're approximating a distribution that looks like this with something that looks like this, then a lot of stuff can be missing. And there's actually no bound to how much stuff can be missing here. You can imagine a corner case where this distribution is basically constant, just not exactly, just so that it is normalizable. It is still a probability distribution, but very, very, very flat. And then the mean of that distribution can be arbitrarily far in this direction, arbitrarily far away from this point estimate. And that's a criticism people bring up for these approximations. But you have to compare this to what you're doing when you're doing deep learning, which is just to return that number. And so my argument is going to be giving you this is still better than just giving you this point. And I'm going to make that argument many, many times more in the next 2 or 3 lectures. Just this is the first time I'm bringing it up. Question?
Do we now approximate by one distribution or are putting distributions on several points throughout the space?
So the question is, are we approximating with just one distribution or are we putting several distributions in a space? I think the answer to the question from what I think you're asking is no. We're only putting one probability distribution at one point, one Gaussian. So there's no mixture of Gaussians here. It's just a single Gaussian. The nice thing about these types of approximations is that they are purely differential. What do I mean by that? I mean that we can find this approximation using the mechanism that you have encountered in other courses, in deep learning classes, namely gradients and higher order gradients. There's no integrals involved here, no further optimization. Maybe if I have time, at the end of the course, in 2 or 3 weeks, I get to talk a little bit about what you would do to get a better approximation here and why that would be more expensive to do. So your question is, we started with an exponential family which has natural parameters, and we'd like to do inference on those natural parameters. And now it seems like I've done inference on the latent function, which is actually phi of x times the parameters. Yes. So the trick is exactly that there's no sigmoid there in some sense. Well, there is a sigmoid, but it's not in the bit that we do the inference. So we are learning a distribution over, what's a good slide to look at for this? Not sure. So here, this one, right? So this function that we're doing inference on is linear in theta. And what we're doing now is we're doing inference on f, but actually we're simultaneously doing inference on theta, which is easy to do at the same time because of this linear relationship between theta and f. Right? By computing the most likely theta, we're effectively computing the most likely f, because it's just a linear push forward. And now your question is, what about the data? What about the y's? Well, the y's enter through this likelihood function, which is indeed nonlinear, but we're using that in the optimization bit to find a theta hat, which is then also immediately giving us an f hat. And so the only hard part comes in actually when you want to make now a prediction about new labels. If you now want to make predict the next, so if you go to some other x in the domain and you say, what we can now do is we can ask, what is the function? Well, what are the weights? The weights haven't changed. We're now just at a new point. What is the function at that point? It's feature of the new point times our inferred theta. And now what's the label at that point? Is it plus or minus? Well, to answer that question, we have to solve this integral. And yeah, maybe it's not great that I'm not showing you another alternative for how to compute this integral. I'll do that next Tuesday. But maybe you can just you realize that a trivial way to do this integral is just to replace this distribution with a point mass at theta hat. And then you get exactly what people do in deep learning. You just evaluate the logistic off, or the softmax off if it's multi-class. By the way, all of this works the exact same way if you do multi-class classification. It's just more annoying because you need to learn several functions at the same time. And so everything becomes a nasty broadcasting out over some array-valued function. Let me show you some code at the end. And now I actually had wondered whether I should show you this code today or wait until next Tuesday. And now I feel like maybe I should, because otherwise I can't show you what I have on the final slide. So I'll do that. You'll find this code on the Jupyter Hub. I've just uploaded it right before this lecture. And it just maybe is helpful by highlighting that what I've just described also translates directly into some piece of code. So what happens in this code is that, okay, beyond the usual just loading lots of stuff, is I'm first making a data set by loading this trivial toy data set, making it. That's this data set you've seen before in blue and orange. Now I'm creating what you might call a random exponential family, but that's a dangerous word maybe. So I'm just creating a bunch of features. I'm doing this because I want to highlight that the construction here is general in the sense that it doesn't matter what the features are. I'm not picking particularly regular features, not some grid, not some particular choice of features. I'm just creating a random set of centers So they are distributed at random over this domain here. I just have 400 different gray points over this domain. Actually, I'm plotting them somewhere down here. Every gray dot is just a center of a feature. And then I'm using little bump-shaped features that actually they are Gaussian functions, but it doesn't matter. They're just little Gaussian bumps. You can go into this code and replace the Gaussian bumps with some VLU features if you like, or something else. By the way, doing that, I think in some parts of the literature is called an extreme learning machine. Maybe you've heard of this before. So I'm just randomly initializing some features that I'll never touch anymore afterwards. They're just there. And now I'm assigning, so I'm defining this feature function here, which is just a function centered at those random locations of a Gaussian form. I'm defining the sigmoid just for the hell of it. It's actually also in JAX, but you know, whatever. And now I'm making a plot of what the prior looks like. So to do that, I create a Gaussian distribution using our toolbox for Gaussian distributions, which uses a zero mean and a standard Gaussian prior covariance. Then I draw a single sample from that distribution so I can make a plot, push it forward onto the X space. So I multiply it with the feature of some plotting grid. The plotting grid is just a mesh grid. And then I make a plot. So now you see that our classifier, before it has seen the data, if you like this metaphor, it makes a random prediction for the classes. So that's one particular sample from the prior pushed through the softmax or the logistic. And we see that the classifier doesn't know anything about where the data is, basically. Right? Well, except for the fact that I've put the features, of course, somewhere around the data so that they somehow cover the domain of the data. And now I'm training this Gaussian classifier in the way that you usually maybe, or not exactly usually, but it's sort of reminiscent of how you would train a neural network. So I'm defining a loss function, and that loss function, it's down here. That loss function, here. The loss function will be minus log likelihood plus log prior. So that's the negative log posterior. Because why negative? Because I want to minimize, optimizers just minimize typically. So I'm going to do a minimization problem. Otherwise, I would leave the plus here, and then I would have a maximization problem. For the prior, I can't get rid of this now. Here. For the prior, I just evaluate the Gaussian distributions, log probability density function. I'm doing this for didactical purposes to just say this is really just our prior. I'm not talking about what it is. And for the log likelihood, I'm writing down effectively the log likelihood that you get from a logistic. So the likelihood is sigma of f of x. F of x is y times phi of x times theta. Well, I should have called this theta, but of course I called it w. That's bad. I'm evaluating f using the phi's, and then I'm just computing what the logarithm of the logistic is. So if you take the logarithm of 1 over 1 plus e to the minus yf, you get 0 minus logarithm of 1 plus x of yf, which is x of 0 plus x of yf. And there is a nice function in JAX that's called log at exp. So the logarithm of the sum of the exponential of the inputs. And so here the inputs are 0 for the logarithm of 1 and minus sine times f. That goes into our loss. And now I just run an optimizer. So, okay, actually, let me see if I can really run this, just for the fun of it. For that, I literally compute gradients of the loss and do gradient descent. So I've just set the learning rate to 10 to the minus 4, and then I just run this, and you see it run up here. Oh, no, I'm getting problems with Jupyter Hub. It complains about too many updates per second. Otherwise, you will get a smooth update. But okay, we do 1,000 steps. The loss has gone down. I can make a plot of the loss. It's gone down a little bit, not so much, because these features are not so great. It's not a perfect fit. And now I can make a map prediction. So I compute the features of my plotting grid, multiply them with the trained weights, and I get this plot. Okay, fair enough, right? So, yeah, I actually have a slide for this. So, it makes a prediction for the labels. And we've arrived at that purely from a probabilistic perspective, motivating the logistic, motivating the linear form from exponential family perspectives. Hey, it kind of works. Okay, so this is clearly pretty much the same thing you would do with a neural network if you had a shallow neural network with a single layer. Do we get anything else on top of that? Well, we will get two things. The first one I'll do next Tuesday, namely uncertainty on this prediction, which I think is good, right? You would like to know whether you're off or not. And we also get something that I'm going to redo next Tuesday, but I'm going to sneakily show it to you now, even though I know I shouldn't be going fast at the end, but I have the slide here, so I might as well say it. Namely, that we've motivated this class label from Bayes' theorem. Right? So we've motivated this by saying we have a joint distribution over classes and inputs on which we can do Bayesian inference. But that means that we actually have up here a joint distribution over x and c showing up in Bayes' theorem. And there's almost nothing keeping us from turning it around and computing a probability distribution for x given c. So a class predictive distribution. The only thing that's missing is an annoying normalization constant, which we don't know. But that's fine for a plot, right? I'm just going to plot and ignore the fact that there's a normalization constant missing. This idea is connected to a cool paper from 2020 by Will Grathwohl, a bunch of other cool people. Some of you might have heard about. It's called Your Classifier is Secretly an Energy-Based Model and You Should Treat It Like One. I'll talk more about that next Tuesday. But if you just go back to the code, I can show you that you can literally do this in a single line. So the only thing I do now is I'm just plotting the exponential rather than the logistic of the map prediction. That's it. It's the entire thing. Literally just take the exponential map rather than the logistic of your classifier, and you get class predictive distributions from your classifier. So this classifier says class number 1 is wherever this thing is black. So it's almost everywhere. Class number 2 is wherever this thing is black, so almost everywhere. Actually, the joint distribution of x is the exponential of the sum of those two, which is this thing if you normalize it correctly. The difference between these plots is the normalization constant. And now you see that you get a small, tiny distribution for the x's that the classifier actually knows about. Without any further training, just by realizing that you've used Bayes' theorem, so you might as well actually just write it out. No further computation other than taking exponentials. So that's the end, because I'm out of time. I'll recap that on Tuesday again, because I realized it was too fast. What did we do today? Please give feedback. What did we do today? We realized that the structure of deep learning problems, well, so far they're still shallow learning problems, but they'll soon be deep. The structure of shallow learning problems can be motivated from the probabilistic perspective. In particular, the softmax and logistic link functions are just Bayes' theorem. Linear forms for classifiers are associated with the idea of exponential family distributions. Non-linear forms will be non-exponential families. To get a posterior on the parameters of these probabilistic families, in the linear case exponential families, we do Laplace approximations. Actually, that's one way to get a tractable posterior. Why do we have to do that? Because the full posterior is intractable. But Laplace approximations provide one simple way of getting an approximate posterior. There are other approximations that I'll talk about later in the course, but this is a very easy one. And there's another cool little hidden advantage to this Bayesian perspective, which I shouldn't have put at the very end, which is that we can also use the same perspective to create generative distributions for the x's, which is not something you generally see in deep learning. You can just evaluate them everywhere. By the way, this entire construction is also possible if the prior over the function is a Gaussian process and not some parametric model. And in previous iterations of this course, I would have done this. I would have done a lecture on what's called Gaussian process classification. And it pretty much uses the same code and the same derivations. And wherever you have a phi x transpose times parameters, you just have a function value that comes from a Gaussian process prior. And then everything is pretty much the same. It's just a bit more abstract. OK. So with that, thank you very much for being here. Thursday is a public holiday. I won't be here. You shouldn't be here either. And we'll see each other on Tuesday next week. Thank you.